start with the solar system today, and then I'll go on to the Earth Moon system, time. This is all a part of time. And before I come to chapter 9, altitudes, where we start the practical part, before this I will explain you the celestial sphere, because if I do that now, then by the time we reach there, it's all forgotten. Because the other topics may be slightly not directly relevant to the celestial sphere for the time being. Then we have a little bit of nautical almanac, and then the position lines and the practical part start. Twilight also I'll be covering. So this great circle will be in the TCNO paper which you're already doing, and the tides also. So I hope that is clear. Let's start with this one now. Small introduction, parallel plane sailing, and then we'll straight away go on to the solar system. Any questions, gentlemen, so far?
No, sir.
Okay. So we all know what is the shape of the Earth. Is it a complete sphere or not a complete sphere?
The complete sphere.
Not a complete sphere, sir.
Not a complete sphere. How bad does it look? I mean, as a not as a sphere.
Oblate spheroid.
Yeah, oblate spheroid, but my question is, what would you compare it to? If I say in your day-to-day life, a fruit or some sort of a ball or a sphere.
Orange.
Pardon?
Orange.
I'll just turn my laptop. Can you see the whiteboard?
Yes, sir. Yes, sir.
I hope it is bright enough, or we need to do some changes. I hope it's bright enough. Yeah, okay. Now let's see. So slight awkward to work in a crooked atmosphere. How does it look now? Because my hand is not reaching the other end. The point is, it's not a sphere, complete sphere, but at the same time, this length is slightly more than this length. What somebody said, oblate spheroid, looks more like an orange. More like an orange. Can you see the circle I have drawn?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So it is slightly flat at the poles. Slightly flat at the poles. The diameter is about 8,000 miles. So the difference between this vertical diameter and the horizontal diameter is only about 27 miles. The equator side is slightly longer. Now, in a diameter of 8,000 miles, 27 miles does not make much of a difference, does it? So, depending upon our convenience, sometimes we take it as a complete sphere. And sometimes if you want very accurate calculations and we want to go deep into it, जैसे बाल की खाल निकालने वाली बात, then we say no, it is not a sphere. In the simple calculations, it doesn't make a difference. Practically at sea, if you are 500 meters, half a mile here and there, doesn't really matter at sea. So we say it is a sphere. But when it comes to very minute calculations like your GPS and these sort of things, Google Maps, and where 10 meters can make a difference. Nowadays, everything is so very accurate. The clocks, the timing, everything is so perfect. So there, then we have to take the exact shape of the Earth into account, because when the shape changes, then a number of parameters, a lot of dimensions change. But let us keep this thought at this only. We will not go too deeper into it now. We will see during the course of the sessions where we are taking it as a complete sphere, where we are not taking it as a complete sphere. The only point why I mentioned this over here was because of the equatorial region being slightly larger in diameter, the Earth is a little heavier over there. There is more uh, Earth mass over there. Now, this heavy portion of the Earth is causing a slight, very, very slight discomfort to us, in the sense that when the Earth is spinning, you know how the Earth is, in which direction is she moving? The daily rotation, west to east. If this is the west, this is the east. So the Earth is rotating in this direction, west to east. When she is rotating like this, and the speed is tremendous, we don't feel the speed. She behaves like a gyroscope. And how that will affect us and our life, we will see that in one of the topics, a very interesting topic later on. So basically, just remember that it is not a complete sphere. It is like an orange, slightly flat at the poles. The diameter and the Earth mass is more on the equator, and how it affects us, we will see. Now, quickly going through this one little more in detail. Let me say, okay. So once I have done this one, we agreed that the Earth is rotating once every day about its axis. Now, if I draw a line like this, don't mind the slight crookedness because I'm sitting on the side and the board is like that. So the Earth is rotating west to east about the axis which it spins. This axis, where it cuts the surface of the Earth, we call it the geographical North Pole and the geographical South Pole. If you have any question at any point, you ask. Geographical North Pole and the geographical South Pole. The Earth is rotating west to east about its axis. Now, when we navigate, we need our position on the chart very frequently. Out at sea, maybe not so frequently, every 4 hours, 8 hours. But nowadays with the GPS, you have a very continuous position. So don't always relate this topic, this chapter, with what is happening today on board with the GPS. We have to, since we are studying this topic, this subject, we have an exam to pass. We study celestial navigation. Why we do that is a long topic of discussion. We will not get into that. But there are times, when things fail. There are times where signals are giving errors. I'm told East Mediterranean, there are problems. Somebody told me the other day around Singapore, things crashed. So these sort of things happen. There is signal spoofing. There are too many war zones going on. Wrong signals are being sent through the GPS. Sometimes the vessel is made to believe that she is in one position, but actually she is not. So vessels get arrested. These sort of things are happening. And you must always remember that what you have on board is the receiver only. The transmitter is lying with somebody else. Now, if the transmitter is in somebody else's hands, How much to trust that signal will be how much you can trust the person who's transmitting. So there are so many things. Then there are naval exercises that take place. I know east coast of UK sometimes they shut down the all the electronic navigation for 12 hours. Naval exercise. So all the merchant fleet, the fishing fleet, pleasure boats, everybody have to depend upon the basic navigation. So that is why we still continue with this subject. In 2010, probably, I think America had stopped teaching celestial navigation, but again 2015 they reintroduced. They said no, let us not take a chance. So it is still there. So the point why I told you this small story is because when we are near the coast, it's very easy for us to take positions. We have the radar, we have the visual bearings, and if you can see the full board. So let's say if this is the coast, and I take two visual bearings and I plot, I get a fix. Can you see that blue or no? Blue is a little too light. Are you able to see this part of the diagram? The one on the top right
Yes,
corner?
sir.
Yes, sir.
Yeah.
Yes.
So it's
Yes.
very easy to get your position, when you're on the coast, when you can see land, when you can see a light and those sort of things. But the moment you leave the coast, and you are surrounded by water, then you don't know what to do. How will you take the position? Then you start looking around, what have you got with whom you can relate? You can see the sun, morning, evening, maybe you can see some stars, you can see the moon, some planets. So over the centuries, people have been devising ways and methods how to find the position by whatever we can see. Near land, we can see so many things, but away from the land, we can see only the sky and whatever the sky has to offer to us. So over centuries, mathematicians, astronomers, scientists, instrument makers, all these sort of people have been working together. Astronomers give details of planets. The mathematicians help them with calculations. Then there are scientists, and then there are instrument makers, and so many people. They have all been working together and devised so many instruments for us, like the sextant and chronometer and things like that. So we have to make do with what is available to us. The olden sailors, they could see the sun, they could see the moon, and they could see the stars. So they started thinking how to navigate by looking at these things. So when they used to come back, they used to talk to astronomers and these sort of people. Okay, I need this, make this instrument for me, do it like this, do it like that. So then we are on the surface of the water, nothing around us, and what we can see on the top, maybe we can measure the angles, horizontal angles, vertical angles. For horizontal angles, we call it azimuth. We need a direction of reference. The direction of reference is the north, true north, magnetic north, compass north. There is a reference point. Your ship is steering in a particular direction, so you have an angle. Horizontal angle, azimuth. Vertical angle, altitude of the body. The sailors realize there is a horizon, there is a flat surface which I can see. So the height of the body I can measure, maybe. If it is right over my head, it is 90 degrees. If it is on the horizon, it is 0 degrees. In between, there can be an angle which I should measure accurately. Same star or the same sun from different points of the earth will give you a different bearing. So they said we need to measure a vertical angle and we need to measure a horizontal angle. Now, when you measure vertical horizontal angles, you need reference points also, from where to draw, how to draw on the chart. On the chart, when you see land, it's very easy. You take a parallel ruler, put it on the compass rose, and you draw a bearing. But how do you draw the bearings of celestial bodies, which are not available on the chart? The chart is only showing the land or only the water, no sun, moon, stars. Very interesting things. So they started to find a relationship between the bodies and the planet. So let us see what they did to the planet. So once they decided that it is a sphere and whatever the Earth looks like, they said, okay, first let us divide the Earth into separate parts. So they made it one like this, divided into two parts. What is this line which I have drawn? What is this line which I have drawn?
Sir,
Equator.
equinoxial.
Pardon?
Equator, sir.
Equator.
Equator.
Yeah, somebody said equinoxial. Did somebody say equinoxial?
Yes, sir, Ganesh.
Yes, sir.
Yeah, don't confuse equinoxial and equator for the timing. What I have drawn is the Earth. When I come to the celestial sphere, we'll talk about the equinoxial. Can you also see this line is not straight? I've drawn slightly curved for you to have a. Can you see the slight curve down below? It's not a very deep curve, but I've drawn a curve. That is because, you know, it is a great circle. So we come to the question, what is a great circle? All of you have done great circle. A great circle is a circle on the sphere, the plane of which passes through the center of the Earth. Means if this line I slice it into two, I go deep into the Earth, it will pass through the center of the Earth and it will come out from the other side. So it divides both the hemispheres equally. We call this the northern hemisphere and we call this the southern hemisphere. So this line, which is equal distance from the North Pole and the South Pole, we call the equator. So we have designated this as 0 degrees and we have designated the poles as the 90 degrees over the head. So this is a great circle. I will draw one more line parallel to this and one more line parallel to this. What are these lines?
Parallels of latitude.
Parallel of latitude.
Parallels of latitude. The northern latitude, you can see it's curving like this. Southern latitude, I have made it curve like this intentionally. Now, if I slice the Earth at this level, all of you must have cut some fruit, some apple, something like this at times. What do I get? I get a small circle. Because the plane of this is not passing through the center of the Earth. The circle which passes through the center of the Earth will be the biggest one. And all these are called small circles because the plane of this is not passing through the center of the Earth. So these are parallels of latitude, you said, very good. As we go up from 0 degrees, we go higher, 0 degrees. We call this maybe 20 degrees north, and we call this, let us say, 20 degrees south, parallels of latitude. So now we have got a reference point. We have developed a reference point. Let's say if I am here, I am at a higher latitude as I go up northern latitude, and if I am below this equator, I am at a certain latitude and I will designate it as south. So we have developed a coordinate, a reference point, how to give our position. Earlier, the concept of longitude was not there. So people, they used to do parallel sailing. By parallel sailing means they only used to sail either east or west. Sometimes they used to know the latitude of a place after sailing. So they would only sail either go east or they would only go west because it was easy for them to find the position. How it was easy for them to find the position? Because anyone can give me an idea why it was easy to find the latitude for them before they developed the calculations for longitude? Think out of your, apply your mind, see if you can. All of you have done pre-C, all of you have been at C. You must have heard so many things, you must have discussed so many things. You have read your books on practical navigation probably. Why was it easy to know the latitude? You will realize very soon when we are doing practical navigation also. They realize that the pole star remains at a fixed height depending on the latitude. So every day if they used to keep the pole star at the same height, they knew that they are making the same latitude. Similarly, meridian altitude by sun. So let us say the sun is having a north declination. The sun rises here, the sun sets here. By taking meridian altitude of the sun, they would be able to find a latitude very easily. And so then they knew, okay, either I have drifted north or I have drifted south, and then they would maintain the latitude. Same thing they can do with the pole star. If you would have seen the pole star's altitude is the same as the, anyone? The pole star's altitude is the same as the latitude of the observer. So if you are at 30 degrees north, when you look at the pole star, the altitude will be 30 degrees. When you are at 50 degrees north, the altitude of the pole star will be 50 degrees. We will study all these things later on. No problem if you are not able to answer now. There's no issue. But once you are done with the course, you will understand all these fine tricks and things that I'm talking about. There's a lot of small tricks which navigators know. So latitude was easy, so they used to sail east and west when they used to hit upon the coast. Let's say from East Africa they're coming to India, or India going towards Africa, crossing the Atlantic maybe, or wherever. East and west they would go. When they used to hit the land, they used to figure out where they are, and then they used to go north or south depending upon wherever they wanted to go. It was not necessary that they reach the port at the first hit, they would find their way slowly and slowly. Then came the concept of the other ordinate, longitude. So for longitude also we needed some reference point, and then it was seen that if you draw the line from N to S, you can also divide the Earth, the globe. Just like we divided horizontally, we can divide it vertically also. Now what are these lines, two lines that I've drawn? What do you call these lines?
Meridian.
Meridian.
Meridian. Very good. Is meridian a great circle?
Semi-great circle.
Semi-great circle. Because it is only going from north to south, the half part of the globe. The other half on the back side is another semi. But if we continue, then we can call it a great circle. Again, why is it a great circle? Because the plane of it will pass through the center of the Earth. How is it possible that I have drawn two great circles from the same point, north and south? Whereas in the case of the equator, I said only one great circle, and these are small circles. Any idea?
Because
You see
from
the,
pole we can make as much as we want.
pardon? Come again.
As it is from pole, so we can make as many meridians as we can, and it will be a great circle.
Yeah, very good. If you want to make a great circle on any 2 points, remember only one great circle can be made. let us say you have 2 points and you join them by a great circle, only one great circle will be possible. But if the 2 points are on the opposite sides of the diameter, through and through, any 2 points if I take, let us say I take a point here and I take a point here. In that case, I can draw only one great circle. But if I take a point here and I take a point diametrically opposite other side of the sphere, then you can make as many number of great circles as you want. This point is clear? Okay, very good. Now, for the latitude, I already had a central reference point as the equator. I went either north or south of it. But for the other point, for the longitude, as a reference point, they made a meridian which is passing through Greenwich. Let us say this is somewhere here, G. Greenwich is a small place near London. If you are interested in maritime affairs, if you go to London sometimes, then you must go to Greenwich. They have a central observatory over there and the Greenwich Meridian passing through that one. This one was designated as zero longitude. So we call this as zero longitude. And again, if you go through it, through the Earth, it divided into two hemispheres. We called it the Eastern Hemisphere. This is to the east, the Eastern Hemisphere, and this one we call the Western Hemisphere. And the meridian opposite to zero, we call it 180 degree, because after 179 east we say 180, after 179 west we say 180. So now we have divided the Earth into two halves, the northern hemisphere, the southern hemisphere, and vertically if you see the eastern hemisphere and the western hemisphere. So now we have given a naming technique, a naming method. So wherever you are, in whatever position you are, you can always say I am so many degrees, so many minutes in the northern latitude, and so many degrees and so many minutes in the eastern latitude. So everyone has got an idea of this one. Any questions on this? If no, then we move on. These are the basics, so I'm sure there will be no questions. Okay, so I will now quickly take you to parallel sailing. Just spend a few minutes over there. This green is not good. Okay. Equator. Let's say someone has to go from point A to point B. There's a meridian from here, and there's a meridian from here. Okay. If someone is going from point A to point B, he is also covering some distance. The distance is AB. He is going from a longitude, let's say 20 east to 40 east. But is the distance at the equator same as the distance at a different latitude? Let's say 50 degrees north. Is the distance AB equal to the distance CD?
No, sir.
Is it less or more?
Sir, CD is more as compared to A and B.
CD is more as compared to B. You see that the two meridians slowly they are moving and converging at the pole. At the pole, the distance becomes 0. Alternatively, let me say one ship starts from C and another ship starts from D. And they are both steering 0, 0, 0 degrees. One ship starts from C and one ship starts from D. Both are steering 0, 0, 0 degrees. Will the distance between them remain the same at all times?
No, sir.
Let us say they were 100 miles apart. But if both are steering 0, 0, 0, their distance will not remain 100 miles. They are converging slowly and they will finally go and meet at the North Pole. So, as the latitude is increasing, the distance is decreasing, which means there is a relationship between the distance and the latitude. Latitude increase, distance decrease. Latitude decrease, distance increase. So when we have to find our positions, the distance or the the east-west distance traveled will affect our position and how we calculate our longitude. So there is a formula. I will not go into the derivation of the formula. This east-west distance is called departure, DEP. And this distance over here at the equator is called the D long. And the relationship that is developed is departure upon D long is equal to, what is it?
Cos of lat, sir.
Departure upon D long is equal to
Cos lat.
Cos of lat.
cos of latitude. You all must have seen the derivation in the book. If you want, you can go through that derivation. Departure upon D long is equal to cos lat. Just give me a moment. Have you attempted any problems on this out of that Joseph Evari book?
No,
Pardon? There are some very interesting problems given in that book. Have you attempted any of those?
No, sir.
Okay. So if you have time and if you want, you must attempt those questions. After the parallel sailing, and immediately after the parallel sailing. But it will set your mind thinking and it will help you in the entire TCNO, CNO paper, because then you will get the concept very well. Okay. Departure by d long is equal to cos lat. This formula, you will be using it very frequently later on when we do our staggered observation in the practical navigation part and these sort of things. Okay. The other thing which I think I will remove this one now. The other thing which we can talk a little bit now about is the plane sailing. So as in when things develop for the navigators, they also realize that we always cannot go east-west and then a lot of time is being wasted. So definitely they have to sail in this direction because always different latitude, A and B, the position would be in a different latitude, different longitude. So what happened after some time, they realized that they can do better than this one. So we come on to the plane sailing part. A has got a latitude and a longitude. B has got a latitude and a longitude. Okay. If I subtract the longitudes of A and B, I get D long. But this D long is at the equator.
सर आपकी स्क्रीन थोड़ी ब्लर आ रही है.
Blurred आ रही?
हाँ सर, ब्लड आ रही है.
ब्लर आ रही है सर, मतलब
Yes, sir.
प्रॉपर्ली दिख नहीं रहा है वो व्हाइट बोर्ड का.
व्हाइट बोर्ड नहीं पता चल रहा.
Okay, 1 minute. How's it now? I have not changed the position of anything, neither the board nor the laptop.
Sir,
If there
I
is too
think
much
there is
light
a
reflecting, let me
network
try to
glitch
adjust the light.
because the sound is also getting hampered by it.
Yes, sir. Kanishk is right, sir.
Is it better now?
Not yet, sir. Kanishk is still right.
How's it now? Better or worse?
Same, sir.
Sir,
As
a
Kanish said,
little
sir,
bit
there is a glitch, sir.
little bit less.
सर स्क्रीन ही ब्लर है सर.
Screen blurred?
Yes, sir. Screen is blurred.
Yes, sir.
Let me adjust the distance. The focus is autofocus. I have not changed anything as yet. I can only change the light in the room. I can either draw the curtain or open the curtains.
सर रिफ्लेक्ट नहीं कर रहा है सर. एक्चुअली स्क्रीन ही ब्लर है. मतलब सर हमें नहीं पता चल रहा कि बोर्ड पे क्या लिखा हुआ है.
अच्छा,
हाँ सर, वो बार नेटवर्क का ग्लिच हो रहा है सर.
My network
सर
is also.
नेटवर्क की प्रॉब्लम है क्योंकि आप बीच बीच में सर अटक भी जाते हो.
But my signal is full. Network
सर मे भी आप एक बार लीव करके वापस ज्वाइन कर लो सर. वापस हो जाए.
Let me see. The lighting is enough?
Yes, sir.
यस सर.
lighting
लाइटिंग ठीक है.
यस सर, लाइटिंग ठीक है.
Okay. So you want me to leave and join the session again? Will it help? I don't know. But whatever it is, the screen should not be blurred, no? I can change the distance I can bring it closer and then see how it is. अभी कैसा?
या सर बेटर सर,
ये
पहले
थोड़ा
से तो
बेटर
बेटर है
है,
सर।
ये थोड़ा बेटर है।
यस सर बेटर।
तो जहाँ पे खराब होना शुरू हो तो बता देना मुझे।
हो गया सर।
हो गया सर, हो गया, बहुत पहले हो गया।
खराब हो गया?
हाँ जी।
अच्छा, अब
सर आउट ऑफ फोकस है अभी, आ गया सर, थोड़ा ये बेटर हो गया, बट अभी भी सर विविड है सर।
और आगे कर देता हूँ। अभी
हाँ सर
सर
अभी ठीक है।
पता तो चल रहा है बट अभी भी विविड है।
ये कब से हो गया अचानक? पहले सुबह तो ठीक था, तुम कह रहे थे।
हाँ सर
सर,
सुबह
मुझे
मॉर्निंग में तो
दो
ठीक
दिन
सही, अभी हुआ
मॉर्निंग में ठीक
ये
था
जैसे आपका प्लेन सेलिंग चालू किया ना अपन ने।
अच्छा, so what do you suggest? क्या solution है इसका?
सर पेंट पे सर हो सकता है अगर इफ पॉसिबल सर।
Pardon?
पेंट पे सर, अगर स्क्रीन पे ही आप उसको मतलब ऐसे एक्सप्लेन कर दो तो।
पेंट पे थोड़ा उसमें स्लो हो जाएगा, इसमें थोड़ा जल्दी काम हो रहा था।
सर उसमें सर एक्चुअली क्लियर होता है सर, और कुछ
हाँ, that I
नहीं।
understand, of course. Yeah, but I was told that this is better, I should do this way. So that's why I picked up this method. Actually, तुम लोग ब्लड का इशू ला रहे हो ना, तो ब्लड तो फोकस से होगा। फोकस, चलो लेट मी लीव द सेशन एंड आई विल कम बैक अगेन इन अ मिनट। अभी देखो कैसा लग रहा है?
ब्लड आ रहा है।
अभी सर क्लियर है सर, क्लियर आ रहा है सर एकदम
है सर।
अभी
अभी
सर दिख रहा है सर।
क्लियर है।
साफ दिख रहा है सर।
अभी से क्लियर आया सर।
वेरी नाइस सर, वेरी
हाँ
नाइस।
सर।
यस सर अभी क्लियर हो गया।
अचानक कैसे क्लियर हो गया?
थोड़ा नजदीक ले लो सर बोर्ड बस।
वो नेटवर्क का इशू रहता है कभी कभी सर।
नजदीक लूं या ठीक है रहने दूं अभी?
तो आगे ध्यान देते हैं, सही है।
एनीवे, तो ठीक है। So but we know that, you know, we don't always steer east and west. We steer any course that we like. So we come to plain sailing now. So if you are going from point A to point B, D-lat or D-long तो हम लोग निकाल सकते हैं, because when you are going from point A, you will definitely know the position of point A, lat long, and when you are going to point B, you will definitely know the position of point B also. So D-lat D-long तो तुम निकाल लोगे, ठीक है? बट इस ट्रायंगल में क्या हम VC को D-long बोल सकते हैं? Because they are not on the equator, we cannot call that D long. We have to call it, what do we call it?
Departure.
What is the distance that we are traveling? A to
From
B.
A to B.
So this is the distance that we are traveling, A to B. But the gap between B and C is not the D long as a distance. But position से तो D long है. A और B का difference निकालोगे तो you will get the D long. But A and C is definitely the D lat. So a parallel which is drawn from B and a parallel which is drawn from A, this gap, if I minus this gap, I get the D lat. Now all distances are measured on which scale? All distances are measured on which scale?
Meter scale.
Latitude.
Latitude scale. So in chart work also you must have noticed that whenever you have to measure the distance on the chart, let's say if your chart is somewhere here, you will measure the distance along this D lat. But if your point of reference is somewhere here, you will measure the distance across that one. Why we do that? We'll come to that in a moment. So if this is the vertical line as a meridian, that means this is pointing 0, 0, 0. So what does this angle become? If you are going from point A to point B, this becomes your
Course.
course. This becomes my course. So there are 4 important things in this triangle by which we can, if we have 2, we can find the other points that we need, other coordinates. Mainly we are interested in the course and distance because we have to go from point A to point B. So what important formulas we get out of this? Tan course is equal to
Departure upon D lat.
departure upon D lat. How do you find departure? The formula is given on top. What other thing we are interested in? Distance.
Distance.
Distance is equal to
Departure upon sine course.
distance is equal to,
Departure upon sine course.
yeah, but departure sometimes you may not have. The formula which is commonly used is distance equal to D lat into
D lat upon cos course.
D lat upon cos or D lat into secant cos. This is a very accurate formula and this you will find it is being used everywhere. Why I say accurate and good one? Because D lat you can never go wrong. D lat will always be there. Wherever there's departure, then either convert from D long to departure or whatever. So distance is equal to D lat into sec course is a very good formula which generally we use. Okay. In your Mercator sailing, we have the formula slightly different. Tan course is equal to anyone?
D long by DMP.
Tan course is equal to D long upon DMP. There we have another triangle where we call this D long, but then the D lat is also extended because that is DMP. What is that? I will just tell you in a moment. In any chart you must have seen. Let me delete this part. In a Mercator chart, you must have seen. Let's say this is a Mercator chart. the meridians are equally spaced. You may find slight difference because of my free hand. The meridians are equally spaced, but when it comes to latitude, as you go higher up, the gap goes on increasing. So this I have intentionally magnified too much so that you can make out. If this is 0, this is 10, this is 20, this is 30, this is 40. You can see the gap goes on increasing because of distortion, and you must have learned all that in your marketer projection. I will not go too deep into that one. But this distance remains the same. Each one is called the meridional part. So let's say if this is 0 degrees longitude and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 degrees east. Each degree is divided equally. And all the small gaps also will be all equal. But what happens in this case? Here if the gaps are with every degree, at every point of time, the gaps are increasing. With every latitude, the gaps are increasing. So the meridional parts, what we are saying, the distances were used by the latitude scale, but if I use this scale, to measure the latitude, then I call it by the meridional parts. So the number of meridional parts from 0 to 10 will be less than the meridional parts from 10 to 20. 10 to 20 will be less than 20 to 30 if I use this scale. Why I'm bringing up this point is because I find a lot of candidates, when they're doing chart work and they have to measure a distance over here. Let's say they have to measure a distance like this. Either they will start from here because they are too lazy maybe to bring their hand up. But the correct distance you will get if you measure along this. Some candidates I even found they were using this scale to measure the distance. And candidates who were going for their second mate exam. So the point is you should be aware of which is the correct scale to be used and how it is to be. Otherwise your answers will all be wrong. And the examiners, they always check the papers thoroughly and properly. They have got enough time. And if he realizes that you have used this scale to measure the distance, then definitely you will lose many marks. He might give you some marks for the concept, for the procedure, but definitely he will deduct many marks because you have made a principal error. So gentlemen, any questions so far in the small introduction that we have had? I'll be closing this introduction now and I will be starting solar system.
Sir, we should use latitude scale to measure distances.
Yeah, distance is always measured on the latitude scale.
Okay,
In the practical also we will come see, even though this may be a purely TCNO topics, but I generally briefly touch upon these because when we come to practical navigation and when we do staggered observations and when we have to plot the staggered observations, you are basically creating a small Mercator chart on your plane sheet. So when you're creating a small Mercator chart on your plane sheet, then having an idea of all the basics is slightly helpful over there. So that is why I briefly touched upon these topics today. So, and it was just to get an idea of where all you stand, basically because there has been some gap. There are tough times and very difficult times going. So since I was starting today, I just wanted to make sure that we are on the same page. So we can take a 15-minute break now, gentlemen. It's 10 o'clock. 10:15 when you come back, we'll start solar system. Is that okay?
Thank you.
Okay,
Okay, sir.
Okay,
Thank you,
thank
sir.
you, sir.
Can take a break now.